still hear me like this? Just fine. Test, 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 test. Yeah. Yeah. I got you. Do we want to move another tail for the projector so they can see it? Okay. All right, so what problem is this going to be? We have a UV axis, but what laws are we going to start using in this problem? Yeah, so cosines, loss signs, we're going to try to go in that direction. So for the first one, let's get the magnitude of the components on the v-axis. And, all right, so you can read that. All right. So the general setup for the first one, 2-5. What I did is going to be f1 of v over sine 70 minus 30 equals f1 sine of 180 minus 70. Can everybody read my writing? All right, so this is lost signs, right? Using law of signs. So where did I get these numbers from? What did I do? You guys remember? This is a long time ago. So when we're drawing our free body, does everybody see how I did that? So what law is this? Parallelogram law. So we can't really use just sine, cosine, tangent directly because we don't have axes with 90-degree angles. Since our u and v are off, we're going to have to use law of cosines and law of sines and do parallelogram law. So here, so our f1, and we're always doing the angle opposite of the force. So that's our 110. So 180 minus 70 is 110. So that's where that comes from. Now we're looking for our f1 on the v-axis. Or did I just do u first? U. So I did u first. F1 on the u. Sorry, my v's and u's look similar. I even get myself sometimes. So this is going to be f1u. And 70 minus 30 is going to be this angle right here. So the 70 right there. So looking at the geometry of the problem up here, this is a total of 70, right? So this has to be a total of 70 just using geometry. All right? And the remainder right here is going to be that 40. It's right here. And it's going to be the opposite angle, and that's why our f1u is over sine 70 minus 30. Everybody see that? All right. The overall answer for this one, you rearrange for f1v, and your overall answer, we got the time. I'll just rearrange for f1v. or U, sorry. Rearrange, solve for F1V, or U. Anybody have any questions on that? Anybody have any issues with the geometry and how I got it? All right, so now we have to find the V component of F1. So we're going to just do the same thing. Rearrange. And get our answer. Is everybody good with that process? Just a simple algebraic as soon as you understand that you can use log sines or log cosines. Log cosines would have been longer though. So now it wants us to break down the components of F2. So now we have to do our another free body. So once again, we set up the parallelogram law, just drawing our dotted lines there, and then we're going to go right into law signs again. So shorten it up a bit. That'll be U. Okay. So that's the whole law signs equation. And since we have two knowns here, we can just pick and choose which ones we want. And then that's how that's going to go. So we can solve for F2U, which I'll just write down and then F2V. Okay. So yeah, all you do is just pick the one you want, take those two out, and just cross multiply them, solve for the unknown. That's all we're doing with that. And those are your answers for that part. Any questions? Any issues with any of the geometry? Geometry is the hardest part of this problem. All right. All right, we'll move on to chapter 4. Once again, I'll give you guys about 5 minutes. Just look it over. Try to complete it. Well, you can't complete it in 5 minutes. If you can, you're going to be fine on your final. But start going through it. After 5 minutes, I'll go through it with you. It's going to be on a Study Union WordPress site. Yeah, you can. I'm passing around a little satisfaction survey about Study Union in general. So if you could fill it out and just hand it back to me before you guys leave, I'd appreciate it. Thank you. Yeah. That good? Yeah, man, sorry, it's just small. So. Yeah, if this was small, everybody over there would be screwed. And we'd be able to see shit. You're going streaking.
What am I doing here?
I didn't know there was a roller coaster in the student union. Yeah. Please remove the camera. Are you able to see it while I'm standing there?
Yeah, just what I was thinking.
If you move it right here, if the cable reaches. Because there's no other place for me to stand. Yeah. Yeah, there's just no place for me to stand other than that one spot. If you want to try to move that over, yeah, unless it's already coiled up. But even right here, you would be able to see more of the screen. All right, we'll start going through this. So down here, you see Cartesian. So naturally, what are we supposed to do for this problem? You're supposed to do a whole unit vector process. All right, so first step. Calculate the position. So we're going to calculate the position vectors. All right, so from here, and make a little free body diagram. Right, and we're always going to go from the origin. This is C, this is point B, and then we have F coming off here. And F is right here, so I'm not going to rewrite it. Don't forget about your distances. And for you guys' test too, I don't know about you, but I don't think I really actually got a single statics problem ever right, because I'd always miss a negative or something like that. So the more work you show, the more partial you're going to get. Even if you get the answer wrong at the bottom, if they see you just missed a negative or something like that, you're going to get the majority of the credit. So try to show all your work. And at the end of the test, if you're running out of time, just go for it. Just put as much stuff down on the paper as you can. Just go for partial. All right. So let's calculate the position vectors from there. So we're doing everything from origin. So, sorry, this is A, not O. Why do we only need AC and AB for this? What is the question asking? It wants the moment around AC, right? And what's the overall moment equation that we need for moment of that AC? Anybody remember? Okay, so moment about AC is going to be UAC dotted with position vector AB cross multiplied with the force, right? So just simple moment formula. I don't think a lot of professors let you have equation sheets for statics, so you might want to remember that one. But so we need the position vector of AB, and do we need the position vector of AC? Yeah, why? Because we need to make the unit vector out of AC. All right, so the position vector AB, I didn't put it into a formula because we're starting from origin, right? So literally all we're doing is tracing out the X, Y, and Z axes from origin. So does anybody have any issues with that? No? Okay. Now let's get the position vector of AC. All right, and the way I like to do it is I just like to get the magnitude right after that. And then we go into the unit vector. What's the formula for a unit vector? Position over mag. Position over mag. So it's just going to be AC over mag AC, right? So that just leaves us with 4I over 5 plus 3J over 5. All right? And that's going to be our unit vector. All right. So we have AB, we have unit vector AC, and we have force F. So we can go ahead and solve for the moment. I'll be kind, and I will do the cross multiplication for you guys. All right, so from here, our unit vector, obviously 4I over 5 plus 3J over 5. Vector AB, or position vector AB, 4I plus 3J minus 2K. we'll just put that in parentheses. It's going to be crossed with the force over here. 4I plus 12J minus 3K. All right? And then there's going to be another parentheses out there. Now, this is a dot product in here, but what I like to do, if you don't want to do a 3 by 3 cross multiplication on the exam, all you're doing is cross multiplying these, and then you're dotting this into it. That's all a 3 by 3 cross multiplication is, or a 3 by 3 matrix is. So it's going to look, so the 3 by 3 itself is just going to look like this. 405, 3 over 5, 0, 4, 3, negative 2. And then 412, negative 3. Right? But in reality, all you're really doing, if you want to simplify it, is you're just doing 4I plus 3J over 5 over 5, dotted with a 2 by 2, or a 3 by 2. So 4, 3, let me put it down here. And you're dotting it with 4, 3, negative 2, 4, 12, negative 3. So you can simplify your cross multiplication and just do this, do the x again, do the x again, if you like doing that method, and then just dot the unit vector into it, and then you're good. If you want to do it that way instead of doing a 3 by 3. Yeah. All right. So after that, that's going to equal 4 over 5, negative 9 plus 24, minus 3 over 5, negative 12 plus 8. This total is going to be 14.4 pound-foot. This is the total. What was the question asked for? It's asked for to express in Cartesian. So what do we have to do with this total? What do we have to do with this? Yeah, we have to remultiply by the unit vector in order to get into Cartesian. So MAC is going to equal unit vector AC dotted with MAC, which will equal 11.52I plus 8.64J. And that's our answer. Oh, sorry. All right. Any questions on this? It's pretty straightforward. No? All right. Everybody's good? Move on to the next one. This is going to be from chapter 6. Once again, I'll give you guys about 5-6 minutes, unless you want to try to solve this here. I'll give you a little bit longer. If not, last one was chapter 4, yes. So yeah, this is a roller, this is a pin. This one's the pin. All right. So in any of these truss systems, what's the first thing you should really look for? Well, you can do the members you need, but what's the very first step? And that makes the whole process easier if you find them. You got reactions before that. Zero force members. You get the zero force members, you just cut them out of the problem entirely because there's no force in them, right? So that's one less force. But in this one, is there any zero force members that strike out or jump out at you? No, there's not. If we didn't have a force here, would we have one? Yeah, it'd be right here. We'd have a force here and here, but there'd be no force in the vertical. Everybody see that? Okay. So yeah, first step, look for zero force members. But there are none. All right, next step it would be support reactions. So how do we get our support reactions? What do we treat the truss as? We treat the truss as a rigid body. This allows us to actually get the reaction forces in G and A. But do we need the reaction forces at G? No, why? Because we can cut straight through. So we know of two methods, right? What are the two methods for solving a truss? So sections and joints. Can you solve this with joints? Yeah, you can. Do you want to do all that work? No, you don't. So if you notice that they're all through one area, you can say, all I need to do is cut it. But once you recognize that cut, which side are you going to start on? Does it matter? Can you use this side or this side? You can use both sides, but one has a lot less work. Why? If we had an actual horizontal force going there, then you would be right. It would reduce the force. However, there's not going to be any forces in the x direction for reactions because when we treat the truss as a rigid body, we're only going to have y reactions, right? Because right here, do you see any external forces in the x direction? No, so that we're not going to have any reactions in the x. Will we have reactions in the x in the truss? Most likely. But we're not going to have the reactions have any x forces, right? So you can do it from either side for your section. You can either cut it here and incorporate all of the right or incorporate all the left. Why would we want to do the left? There's just less to calculate. We don't have to take into account all these forces in order to get there. Because if we do method dissections, we have to incorporate a moment, right? So doing a moment for these four, or we just do the moment for the one.
You were saying though, if there's like an external like horizontal force, then you should take it from the right side?
It might be easier, but you still only have one external force over here. So I mean, it would have to change, and there'd be several different things going on. All right. But yeah, so we're going to look at the left side because there's just less shit over there. So we're going to start there. Did I swear? Oh. My bad. I need a beaver, man. All right, so sum of forces in the x equals 0, right? We have no external forces in the x direction. So if we're going to start over here by A, where are we going to take our moment? All right. So we're going to get gy and ay, but we don't need gy, right? So can we just take a moment about g and get a? Right? Yeah, so I mean you can take a moment around a, get g, but there's no point because we've already decided we're going to do sections on a, right? So all we need is the reaction force at a. Moments about g. Again, don't forget to label your moment. They'll take up points. Yeah, so, well, what do we do when we actually calculate the reaction forces on a truss, right? We're treating the truss as a rigid body, right? So all we're taking into account is going to be the external forces on the truss, what are the external forces? We have these, 5 down here, and the reaction forces are the externals. So since there's no other thing besides the x reaction force, we're in equilibrium, so AX would be 0 because there's no other external reaction force to react to. Make sense? All right. All right, so this is a good size equation. Okay. 2004, 2008, 4012, 3000 at 16, 3000 at 20. And we have AY at 24. And that's our moment equation. And we're going to say all of them are pushing down in the counterclockwise motion, so we're all positive for all these. But we're saying our reaction force, our default is pushing up, so that's going to be counterclockwise, so that's negative. Questions? The best way to do this, for those of you who've never been in any of my sessions, is we're taking the moment about G, right? So either put a pen there or your finger. So all these forces are pushing down, right? So push the paper down. Which way does it rotate? Counterclockwise. AY is pushing up. Which way does the paper rotate? Clockwise. So you can even just put your finger on the force, and the paper will rotate in the direction that it is. So that way you're not actually there in the test doing one of these. You know? Everybody's taking physics. All right, so our AY is going to be 7,500 pounds. Does anybody disagree with that? I don't know if anybody did a calculation. Is right? All right. All right, so that's our AY. So what's our next step after that? So we're going to cut it. So we draw a free body diagram. Now, technically, I was bad about it. We should have made this a rigid body and made a free body diagram out of it. I did not. For your test, for all you guys' test, the professors are going to be looking for that. So you're going to have to do a free body diagram to get the reaction forces, treating the truss as a rigid body. And you can do that just by, you don't even have to draw the internal structure of the truss if you don't want to. You can just do it by doing something like that and just having two reactions. And then all the external forces pointing down. All right? So because we're treating it as a rigid body, none of the internal stuff matters at that point. But now we're going on to method dissections, right? And we're going to take our method of sections down through LK, LC, and BC. Everything that they're asking for. All right, does anybody object to that free body diagram? It may not be the most nicely drawn thing, but nobody said we had to be artists doing this. So, all right, so I have my FLK, FLC, and FBC. Go ahead.
Did we not draw any forces on where AY is? Sorry, that triangle where, the triangle where AY.
Right here?
Yeah.
Okay, so what happens when we're doing method of sections?
Cut it.
You cut it, and what happens to those members? They become forces, right? Because we're internal forces. We're worried about internal forces. So if we were up here and say I cut here, what am I doing with all this? You treat it as a rigid body. This is the beauty of method dissections. You cut it, and those things that you cut only become the reaction. So everything else you treat as a rigid body. So you don't have to worry about like joints where you go in per and finding each one. All right. All right, so, and then we have L, A, and B. All right, so we have the geometries, right? Now we have to find the angles. So we have to find theta right here. How do we do that? What's up? Tangent inverse, sorry, yeah. I apologize, I'm a little hard of hearing, so. So theta is going to equal the inverse tan of what? Okay. Which is going to be at like 36.8, all right. 0.8 degrees. All right. So we have that angle there, and that makes that angle 36.8. Does everybody see that? Does anybody have any confusion how I could drag that angle up there without calculating? No, almost. If you're looking up here at the truss, we know these are collinear, right? And this is parallel with the ground. So we can draw a dotted line here, right? So this is parallel with that. So that leads us to say this has to be theta. Make sense? Yeah, this member and this member are collinear. So when we're coming down here, if we just from L make something parallel with the bottom members right here, that means if this is collinear with that and this is parallel with that, then this has to be theta. Make sense? Just a little play with geometry. All right. All right, so we can solve for one of the members right off the bat. Which member is that? So AL is part of the rigid body, remember? So when we do sections, everything that we don't cut and looking for the internal forces for gets treated as a rigid body. So we actually ignore it. So we're looking for these forces, right? Can we actually solve for a force right off the bat? Yeah, we can solve for BC right off the bat doing what? No, we want to start with moments. Because moments are going to cancel out two of the forces, right? Yeah. About L, it will give us BC. That'll be the easiest one to start with. All right, so come over here. Don't forget to put your convention on there. Sum of moments about L. Negative AY. At 4 plus FBC at 3. Does anybody have any issues with the setup? From now on, to save time, I'm probably just going to leave AYs as AY because we already solved for it up here, and just for you guys to know so you can just plug it back in. All right. And then it's going to be solved with FBC is equal to 10 kip. And is it going to be in tension or compression? Tension? Okay. And why? Because it's positive, and our convention said it was in tension already. So we're just going to leave it as is on the free body diagram and say it's in tension. Now, where do we want to go from here? What's the next good place for a moment? Okay, about C. So even though it's not there anymore, C, the vectors still point to it, and we know the geometries of where they intersect. So we can have distances to make a moment from. So we take our moment about C, we're just going to kind of be imaginary in here because we're dotting it out, and we're saying that's where the vectors intersect. Does that make sense to everybody? Right. Moment about C. So 3,000 at 4 minus AY at 8. And then we're going to do this FLK cosine theta times 3, and then FLK sine theta times 4. All right. So everybody understand where I got these numbers from? So when we're doing our trig, we need perpendicular distances, right? So we're using this theta right here. And since FOK isn't perfectly perpendicular, we have to break it up into components, right? So we have to have FLK in components. And it doesn't matter where it is, right? We just have to have a perpendicular distance to a force that's around there. So a concept would be, doesn't matter where this force is, if it's up here, It does, if it's along this line of action, that's the perpendicular distance for the moment. I can have the force here, I can have the force here, I can have the force here. It doesn't matter. The perpendicular distance does not change, so therefore the moment does not change as long as the force does not increase. Does that make sense? Is that confusing to anybody? No? All right. So I separated it up, FLK, into x and y components. And that's what I did there. All right. And then FLK is going to equal 10 kip as well. Tension or compression? Huh? Tension? It's compression. So we get a negative. So it's in compression. So actually, when you do it, it becomes negative. Yeah. So either you can leave this as a positive and put C, and then go back over here and update your arrow, or leave your arrows the same and leave this as a negative and label it still compression. Okay, so if we break it up into x and y components, so is there a perpendicular distance from C to x? So just think about it like this. Now we're turning it this way, right? So if C is way over here and x is up here, we're just looking for this perpendicular distance. It doesn't matter if it's on anywhere on the line of action. If there is a perpendicular distance from the point you're taking a moment to that force, that's your moment. Does that make sense? So up here, our x is right here, and our perpendicular distance is 3. Because from here to here is 3, so it'll still rotate. If you have any questions about if something will rotate, take your pen, and then so I have an x component and see if it rotates. I have a y component, see if it rotates. Okay? So just it gives a little bit of a visual. If you have any questions about it, just put your finger on it, try to push it. All right? Question? So FLK, FLK. Yeah, so they're both, man. Yeah, so I had an x and a y FLK. And that's why the cosine and sine theta were there, which we saw for sine theta over here. And I'm sorry if the parentheses fuck with you a little bit, but it doesn't matter because we're all multiplying together. So it doesn't matter where I put the parentheses. It's all going to be one big mess. All right. And it's in compression. So what I like to do is I just like leaving it a negative and moving on, so I don't get confused when I update my free body diagrams. There's been a lot of confusion for me if I go back and start updating my free body diagrams and trying to make these positives, because I get all confused. What's up?
Could you use like the cosine of FLC and like summarize at the same time as like FLK? If you're taking these into account.
Yeah, so when we're going to solve for that one next. Yeah, sorry. Yeah, because by doing this moment, it means we can just do sum of forces to solve for that one. So we only need one component. All right, does anybody have any issues with this, or tension or compression? We'll move on to the last member. All right, so for the last member, we can just say there's only one unknown, so we only need one equation. So let's stick with the sum of forces. It's a little bit easier. Sum of forces in the y equals 0. We're going to have equals FLK sine theta, because we're doing the y component, minus FLC sine theta, again, y component, minus 3,000 plus AY equals 0. So we only have two forces here that are going to have a y component, and that's going to be FLK and FLC. and we times it by sine appropriately to get the y components of both. Theta is here again, FLK is here, and we're solving for FLC. So FLC is going to be 25 kip. Tension or compression? You got a 50-50 chance, man. It's compression. All right, so, and I don't update my free body, so I just threw a negative in there. Now, if you're going to do this properly, once you get all your negatives, you go back and update your free body diagram and make everything positive. But if you're short on time and you just leave it as a negative, that means the vector you chose here, it's in the opposite direction, and they can actually follow your work. So if you leave it as a negative in this force right here, that means this direction is opposite, so you don't have to update your free body. All right? But if the professor says you will update your free body, update your free body. All right, so, and then here are the answers. And then if we did KJ and CD, what would you do? If we needed to find KJ and CD. You just do the same thing. Just cut it down the middle. Make another section out of it. You need to do that, or you can just take a joint here and a joint there. Don't matter. All right. Got any questions about this? If you have the opportunity, use method to sections. It's a lot quicker than method to joints. Some of the harder problems, you'll have to use a combination of joints and sections, so be aware of that. No, sorry, yeah, -25, yeah. Questions? All right. All right, we'll move on to Chapter 7, everybody's favorite, shear and moment diagrams. All right. It's all good. You can get it out now. I've sworn plenty of times during a test when I've flipped the page and solving a problem. All right, I'll give you about 5-7 minutes to look it over, try to start it, and get through the problem. Is that close enough for or zoomed in enough for everybody? All right. You're kind of squinting, man. I could get your chair up here. All right. All right, so we'll start this. All right, so we can answer this concept question right off the bat. What should the moment at pin B be? 0. Why? Because it's a pin. No moments at a pin. All right, so we got to start by solving for the reaction forces, right? So how are we going to do that? Do we do it all at once? Yeah, we have to split it. Why? Because it's in sections, right? All right, so let's get BC. All right, and what do we do with distributed loads? We make it 1 to get the reaction forces. And remember, when you're doing your shear and moment diagrams, be sure to leave this as a distributed force once you start drawing your shear and moment diagram. It has to stay a distributed force once you start drawing your shear and moment diagram. If you're confused about that, we'll go through it in a minute when we get there, and you'll see why. All right, anybody have any issues with that free body diagram besides the measurement not being on there? Anybody have any issues with the free body? Nope. All right, so now we're going to move on to solving for BY and CY. Next, so let's go on counter. Or that's minus, sorry. Minus. Anybody have any issues with that? No? Because where's the centroid of the rectangular distributed load? 10 in the middle. All right, so we end up with BY equal to 316.67. And then we'll go to solve for CY, or we just do sum of forces Y. BY plus CY minus 150 times 6 equals 0. So our CY equals 583.33. Anybody have any issues with those? Nope. All right. And now we can just treat the entire beam as 1 because we have CY. So when we do that, anybody really want me to draw that free body in order to save time of the big one? No? Okay. All right, so we're doing the entire beam now, and we're going to start with a sum of forces at Y. So entire beam. And sum of forces of Y equals AY plus CY minus 700 minus 150 times 6 equals 0. So our AY is 1016.67. So now we have all of our reaction forces. Actually, no, we don't. What's this? It's fixed, right? So we have a moment. So now we have to solve for the moment. Sorry. I'll zoom out a little bit. There we go. All right, so now we're going to do our sum of moment at A. It's going to equal MA minus 700 at 8. 150 times 6 at 12 plus 6 over 2 minus 800 plus CY at 18. Sorry if it got a little crunched at the end. All right, so we're looking for MA, and then here are all the additional external forces acting on there. The 700, right? Yeah, 700, CY, and the distributed load. 6 over 2. Yeah, so, yeah, half of 6. So 12 plus 3. Oh, my bad. All right, so when we solve for MA, it's going to equal 9,400 pounds per foot. All right. I'm sorry? Right here? Oh, CY at 18, so the full length. This one? 6 over 2. So since it's distributed load, we're still treating it as a single force like up here. So half of 6. All right, so now we're going to proceed on and start sectioning it off, and we need our equations for shear and moment. All right? I will not be doing the integral method here. The integral method is faster, but a lot of professors skip it, so I will not be teaching it. All right, so first we're going to section off. Does it matter which side we start from? Over here? No, it doesn't. We have to do the whole beam anyways. So I'm just going to start from the wall. So section it off. Start it. So our first section at A to right here. Right before the load, it's 700. All right. So we have a moment, MA, AY, and then our X is here, right? So we're going to treat it as a variable because we want the equation. We don't want an answer right now because the equation is going to help us complete the shear and moment diagram. And then what's our convention for shear and moment? For left-hand side? Down and always separating it up and out. All right. So we just call this point D. Just call this D. All right. So this is VD and MD. Not that VD, please. And then, yeah, so let's start making our summation equations. So our VD is going to be equal to our AY. Why? There's no other Y forces. So our shear in this cut is going to be equal to our reaction force at AY. So that's easy enough. 1016.67. And then our moment, we're going to take our moment about D to find our moment. MD. All right. And this is our moment equation. So this we can solve for any point on that line. So this is the main equation we're looking for right here. So if it says solve for the moment equation, this is the moment equation, leaving a distance x as a variable. You could. It's just a little bit more, it's harder to interpret, because if you just start here and just literally leave all your distances as x, then it automatically just pans out when you do your sum of forces.
So like you're solving like over, so you're not going to do it back.
I will, but this is important because now you need to know x-intercepts. So where does it, if it's an unsymmetric beam, where does it intercept the x-axis? So if a lot of your guys is what the homework problems, they're all symmetric and they're rectangular loads, so you're just like, oh, it's right in the middle. But now this isn't symmetric. So where is it going to intercept the x-axis? Because when it intercepts the x-axis, what does that mean? Yeah, that's the max moment. So in order to get your max moment, if the question asks for it, you actually need the equation. So in order to get the x-intercept, you need your shear equations. And in order to get your max moment, you need to get the distance from the shear equation and plug it into the moment equation. I'm sorry? Yeah. Yep. I'll give you a second to copy that down. Yeah, let's see if we can. Okay, so now, sorry if it's getting in the way. I just want to kind of show you this as I'm doing the equation. Here's our x. So this is our x distance for the shear moment, right? Shear, moment. Draw the dotted lines just down. Wherever you see a reaction or some kind of external force. And does anybody know why? So, go ahead. Sort of. So, when you're looking at this, what is this? What kind of equation is this? It's an equation of a line. So when we're actually over here, this equation of the line is going to dictate how this looks. So now this is just the reference to calculus, because now this also gets into the integration method, because now you have your shear equation, and all you're doing is integrating this to get that, while taking into account the starting point at the reaction. So our concentrated moment is over here, right? So if we have a y equals mx plus b, right? Our m's our slope. So here's our slope. And then the negative 9400, well, that's going to be our b, because on the moment graph, that's where we're going to start out, because that's our concentrated moment. So all of these is the equation of a line. And that's all you're doing over here for shear and moment. All it is calculus. You're just making a graph. So now we have where it starts, right? So it starts at 9400 because at x distance of 0 at the beginning, we're at negative 9400. Right? Now how do we get where it ends? Yeah, you just plug in 8, right? Because that's where the line changes. The line is going to change at 8 feet because now we have another external force reacting on the system. So our line's going to change. So up here for shear, we jump up because of the reaction to 1016. I'll leave the decimal point off for now. And because there's no external reaction or anything happening there, we're just going to leave it constant, right? Oh, sorry. We're going to leave it constant. We'll shade that in. All right. If we were to integrate this, we would get this equation. And where do we get where this ends? We plug in 8. At x equals 8, our moment's going to be negative 1266.64. And this is going to be, since this isn't x squared, right, this is going to be a linear line on the moment graph. So we're just going to here. All right? And that's how that plays into it.
Supposed to put number 8, right?
Yeah, so at 8 with this equation, we're going to get negative.
They got a different number, like a positive.
Right, so negative 9400.
Plus 16, fine.
So this shouldn't be over.
I don't think it's to get
Right, this is positive, right?
Did you put in 16? It's 10, 16. I got like 35, 32.
So if,
Well, this times 8 should be somewhere near.
but
Yeah.
I thought like the shear is a positive and that was the moment to be positive too. So
Yeah, so if you're looking at it, you know this is the right line because it's a positive slope. We have a positive shear, and we integrate it, and we get a positive slope. This doesn't matter. This is just where it starts. When you integrate a flat line in the positive region on the shear, you're going to get a positive slope in the moment. Make sense? All right. All right, so now we're going to go on to the next section, and we're going to go out to the start of the distributed load. So we have our moment, we have our reaction, we have our 700, and then we have our shear and our moment at the end. And this is going to be B and VB. All right? So now our VB is going to equal AY minus 700. Which is going to be 13.67, which just so happened to be what we calculated up here. So BY equals VB, just like over here. All right? Sorry, just like over here. Go ahead. I'm sorry? This moment one? It doesn't cross the x because this is our equation for this section of the beam. The reason why we draw these lines is when the line intersects that point, the line equation changes. So each of these points is going to have a different equation for the line. So you can't have a single equation for an entire beam. Each section of the beam where external forces change or you have a reaction force, you're going to have a different equation for the line. It stops right here at this section because now we're taking into account the external load of 700. And it's going to change this. We stopped at negative 1266.64. Sorry, I should have labeled it. All right, so now that we have that, we go back to our shear diagram, and we go straight down. And then, since we have no other external forces acting on the system, once again, it's going to be a straight line. And this is going to be at 316 point, was it 67? Yeah, 67. All right? All right, and then we're going to do our moment. RMB is going to equal negative 94 plus 1016.67 times x minus 700 times 8 minus x. Does that make sense? Everybody? Oh, sorry. Yeah, so that's going to be the equational line. So you can simplify that and combine the x's, and then you're going to be left with something similar to this. For the sake of time, I will not be doing that. So our MB, so this is the equational line. But overall, what is it going to equate to? It's going to be 0, right? Because that's where the pin was, up here. So we don't have a moment there. So it's 0. What's up? So you take your 700, and since you cut it here, this is x, right here. Oh, sorry, I should have put it down here. So we know this is 8, right? So that means this is x. Make sense? All right. So yeah, it should be 0, but we still have an equational line. So it's still going to be a little bit steeper, but it's going to come to 0 at point B. All right? So when you multiply it by the total distance plus the 4, this equation will be 0 at B. Everybody understand that? Because there's no moment at B, because it's a pin. Make sense? So at x equals 12, m equals 0. And that's why we got left with 0 here. And the slope does change, but I'm sorry, my angles aren't right. All right, so now we move on to the last part of it. Now we're going to do the moment equation for the distributed load, or the section of the distributed load. So we're going to redraw our stuff once again. AY, another moment at the end, 700. Bless you. Bless you. And our distributed load, we're going to have our distances, 8, 4, and then this section is going to be x, right? But since this section is x, we're going to treat this distributed load with variables, x minus 12. All right, so this distributed load equation is now going to be this. Anybody have any issues with that? And don't forget, we still have shear and our moment on the outside. So our shear at C, and simplified, all right, so if you really look at this, 316 is where we left off on the shear graph. So if you're looking at the y equals mx plus b, 316 is the plus b. And then the slope is this formula right here, because it's a distributed load and we're leaving it as a variable. All right? So when we do that, we're going to end up with a line like that. But now, where does it cross the x? Right? So it's unsymmetric. Oh, sorry. Where does it cross the x? So, so you can put the shear equal to 0 and solve for x. Yeah. Yeah, you're on the right track, man. We're all tired, man. It's all good. Yeah, so all we're going to do in this equation is we're going to set shear equal to 0, and we're going to, because remember, the vertical axis is shear. So as soon as it's 0, and that's where it crosses the x-axis. All right? So when you set this equation equal to 0, your x is going to be 14.1. And then once you know that location, you draw another mark right here on your shear and moment diagram, because on the moment diagram, what's that going to be? It's going to be your max moment. So that's where you're going to, the peak of the parabolic arch for your moment's going to be. All right? So we set shear equal to 0 in this equation. We solve for x to get the distance of where it crosses the x-axis up here. And then where it crosses the x-axis is where the max moment or the peak of your moment line is going to be. And we will do a similar thing for the moment. Our moment's going to equal negative 9,400 plus 1016.67x. Right, minus 700, x minus 8, and negative 150, x minus 12, and then you're multiplying it by x minus 12 over 2. That's going to equal 0. And then what you're going to do is you're going to simplify that equation, and you're just going to be left with an x squared x. So you're going to be left with a simple parabolic equation after that. And then in order to solve for your max moment, you plug the distance you got from your shear into the moment, and that'll be the actual max moment up here. So you have the location and how high it goes. What's up? I drew that line because where it crosses the x-axis is going to be the peak of your moment. Here, let me finish the drawing. So this is going to go up like this and then down. All right? Yes. Yeah, you plug this 14 back into this moment equation, and it'll give you your max moment, which that max moment will be 334.30 pounds per foot. All right? So in shear, we set shear equal to 0 because we have a downward distributed load, which means we will have a negative slope. So we know it's going to cross the x-axis at some point, even though it starts here and we don't know what our line looks like. And we get the equation of the line, and then we set shear equal to 0, so we know the exact point it crosses the x-axis. Once we solve for the exact point it crosses the x-axis, we draw a dotted line down through our moment graph. That's going to be the peak of the arc of the moment curve. We solve for the moment equation over here by doing the section method. We plug the 14.1, the distance, into the moment equation to get the number for the max moment. Make sense? See a couple glass eyes. But kind of go over this problem a little bit, go over problems similar to it. A lot of the problems you guys have in your homework are symmetric and not like this. If you do not have a symmetric problem and they ask for the location of the max moment, you have to find an equation to plug it in. So you have to find a shear a shear equation so you can actually find out where it crosses the x-axis if it's not symmetric. What's up? So, but what do we have back here? So it's going to end at 800, and it's going to jump right back up to 0. Well, we have a reaction force, right? So the reaction force just so happens to be the same number as it ended at. This is negative 583.33. So that means that reaction force is going to bring it back down to 0. We are static. There's no additional numbers. Everything's 0. We're good to go. Now you're good. Yeah, so just remember on these more complex ones, if they do give you one on the test, these are most likely not going to end at 0, and you're going to have to pay attention to the concentrated moment or a reaction force at the end of the beam. All right? Here. Okay, so does anybody, well, you probably have a lot of questions. Does anybody have any questions that I haven't answered?
Quick question. In the last part, so you're doing by zones, right? Like zone 1, zone 2, zone 3.
Yeah.
So according to what I see, you got like 3 zones, right? In the last one, there is any particular way that you could start from the left to the right?
Yeah, you can. Well, if you're going to go right to left or left to right, you have to keep it consistent.
Yeah.
You can't just pick and choose.
Okay.
Picking and choosing really gets it confusing with some of your signs, and you might have a opposite sign because everybody's forgotten a negative here, right?
Okay.
Yeah, and it's taking you 2 hours to solve it. Yeah.
When you get the x, the 14.1,
Yeah.
you use the value of b is equal to 0, right? But can I only get in that particular equation, right?
Yeah.
Can I be- alright.
So you're going to solve this. So this equation, most likely what's going to happen. Yeah, no, this is incorporating the entire beam. So like if you're doing integral method, if you really wanted to do integral method, what you're doing is you're treating each section differently. So each section actually starts at 0 in integral method.
0 to 1, 0 to 9.
No, it's 0 to 8, and then it's going to be 0 to 4, and then it's going to be 0 to 6. So you're actually, because you're only concerned about the line with the integral method, because you don't care about anything else. Because you're only concerned about this line, and this line. So that changes. But here, when you do the sections, you incorporate the entire beam. So this equation, when you solve for 0 shear, should give you 14.1. Make sense? All right. Any other questions? Yeah, just take your time on this. If you're going to choose a question on your exam to spend the most time on, usually these are it. So don't save it to the last, but time yourself. If you don't finish in a time limit that you've kind of established for your test, kind of move on and make sure you get these equations there, though. So the big thing is if you get a solution equation, you can draw the graph. So, all right. Okay. This goes to 4:30, right? Okay. All right, so does anybody want to do centroids and integration, or do you want to try to do another shear and moment? You want to do centroids or moments of inertia? All right, moments of inertia or centroids? Moment of inertia? That's fine. All right. Yeah, making sure this is a good one. Here, let's do another one. Do you want to do one that's actually dimension-based, or do you want to do one that's calculus-based? I wish I knew, man. I'm popping smoke after next week, so I would have given it to you. So it's up to you. Do you want to do straight-up integration, or do you want to do tabled moments of inertia? You want to do tabled? Okay, so we'll do this one. All right, look at it for a couple minutes. We might only have time to do one of the questions, but we'll get through as much as we can. Okay. So yeah, let's try to start it a little bit and then go from there. This will be the last one, yeah. It's about 4:10, right? Yeah, it's about 4:10. Yeah, I'll give you a couple minutes.
You're posting these notes also?
Yes, I will. What's up?
I can find you on YouTube. I was trying to.
Yes. All this is streamed and recorded on YouTube as well.
I saw some of them, but I can't see.
I think it's called the study.
Yeah, we just go ahead and
Yeah.
just go on YouTube and type like suck you with this. Let me find this. Yeah, I can find this.
No, this is
Yeah, for the first part of it, since this was the first session, the camera wasn't in the exact, so I'm blocking a lot of the screen for the first couple problems. But now the camera's over there, so the later ones, like the sheer moment, everybody was able to see it. All right. I'm sure that's the one that has more questions than the others. All right, so let's get started with this one. Try to save some time. So can we answer one of these right off the bat? Okay, which one? X is 0. Why? Symmetric, okay. And what about this? All of the above? Yeah, it's D. We don't have enough information. We're only given a 2D axis. So this looks like a 3D, but it's really only a 2D. All right, and then so we're just going to redraw it. All right, we're going to have two pieces. Call that 2, call that 1, right? Go there. Axis going down the middle, 150. This is all in millimeters, all these dimensions, so everybody knows. 150. Thickness is 50. Thickness again is 50. And then that's 250. And up here, as you can see, it wants us to figure out the y bar. All right. So we want to determine the cross-sectional area on the y-axis. All right. So what's the moment of inertia for a rectangle? Base 112, 1 over 12, base times height cubed. Now it's a new formula for you. Yeah, it's going to be in your charts. Yeah. But in later courses, it's going to be beaten into your head so much that you're going to memorize it. So, yeah, it's 1 over 12. I for a rectangle equals 1 over 12 base times height cubed. Now, this in your formula sheet changes height over here, base over here. But if you always look at it as this is x and this is y, y is always height, base is always x. So it always changes. So the height of this is actually 250. The base of this is 50. So if you always think about x is always the base, y is always the height, then you really don't have to screw around with that much. You just fill in the numbers. All right, so IY. So I1, we do the first one. 1 over 12, 50 times 300. It's to the third equals.
Do you have like to add like the area to it?
To the area to it?
Yeah.
So if we're using this equation, no, we don't. So the calculus method, if you're going to do that, when you're just given lines, then you have to take differential of the area times an x squiggly and do all that other fucking shit. So like if we're doing this one, you're going to have to do all that. All right? You would have to do the rectangles, scan in the whole line and stuff like that. But for this, all you're doing is you're taking your moment of inertia for the rectangle in the y direction, which is this is it, because our base is going to be 50, right? And our height's going to be 300 for the overall. Wait, what? Where's the parallel axis? What did I do? Yes, so I'm taking into account the entire. No, right? No, it should just be 250. Yeah, you're just adding them together. Or no, it's 300 right here. Sorry. I was looking at the wrong one. So yeah, 300. Right? And then 50. Sorry, I did it sideways on this other one to try to incorporate this in there to make H and B. So I'm confusing myself. Yeah. Yeah. So we're doing about the y-axis. So what we're concerned about with the y-axis. So we're going to treat this as our base, and we're going to treat this as our height, the way I did it over here. Sorry, I wrote it down a different way. I apologize. And remember, moments of inertia always to the fourth. It's a distance to the fourth. So what do we do with all this? What do we do with these two? We just add, it's a summation of all the moments of inertia. And that's why we don't have to worry about the differential area. Because all we're doing is, since we already have the equation for moment of inertia around a certain axis, all we're doing is adding the two distinct shapes together. So we're just going to add them. So IY equals 1.15. It's 10 to the 8th millimeters to the 4th. And that's the answer for that.
So if they didn't ask us about a specific axis, then we'd have to add on all that
Yeah.
extra shit.
Yeah, you have to do the parallel axis theorem. You have to do that whole thing. All right, so unfortunately, I got to end it here. I will upload all my solutions to the same website that the review is on, so you guys can review it. If you guys are testing on Monday, there's going to be 3 or 4 more sessions before your midterm, or sorry, final.
So for these, it says, there is a number provided left, so say what number would that be?
5. That'd be 5. 5.
There's 2 rows.
There's 2 5s? Just put 0, 5, if you don't mind.
0, 5.
Yeah, just top one 0, bottom one 5. Just top one 0, bottom one 5. It's just yeah, just put top one 0. Yeah, bottom one 5. All right, thank you for coming. Hopefully it was helpful. Yeah, if you don't mind just bringing them up here before you leave, I'd appreciate it.